Okay, good afternoon, everyone. We have Professor Bhandarkar and Gaitonde as well. So I think we can begin this interaction session, the first one in this workshop. So in principle, what has happened so far is that participants have gone through the material corresponding to the first two topics, and we will have some discussion wherein from my side I will pose a few questions perhaps for you to think about, and interspersed with that we will request the participants to present to everyone uh, any questions or problems that they have generated on the material which is covered in topics number 1 and 2, essentially the first 6 lectures. Okay, so as most of you have seen, I suppose, the first 6 lectures set the tone for the course with certain basic definitions and ideas introduced. So let me pose one question from my side. How many of you had heard and knew the notion of a primitive quantity? Somebody who wants to answer can raise hand and go ahead. Yes, Naren, please.
Yeah. So I would say like this way as my response that the word primitive is new to me.
Okay, that's good.
Yeah. So that means the terminology or the coining of the word is primitive. So we have been knowing that, like for example, volume comes from some other concept.
Yes.
The density comes from some other concepts, or like velocity comes from mechanic concepts. The word primitive is something new I have learned from this lecture.
So that's good. So now let us say, I suppose someone else is also mentioning that they didn't hear about it. Now let me pose a question then, that suppose you want to introduce this in the course that you are teaching now. And now let us say I am a student and you want to explain this idea of a primitive to a student such as me in the class. And remember, I have done only up to first year of engineering at the most, and therefore you are aware of my background and so on. So how would you introduce the idea or the notion of of a primitive?
So maybe I would think like I'll just ask the students that you please list the variables that you have known as of now in physics. So somebody will say volume, somebody will say mass, somebody will say velocity, somebody may even say enthalpy, because these are all part of high school physics. So they would definitely say enthalpy, entropy.
But would you then try to explain to that student that enthalpy is something that we will not really be treating as primitive?
No, I'll first list down. I will not tell them what is primitive. I'll just say list. I'll say just come with some, it's like asking them to tell the colors that you know. That's it.
Okay.
And then making them of these colors, only the certain 7 colors is something that we call as part of the rainbow. But first I want them to list what are the colors they know. That's all. So in a similar fashion, I'll just ask them to list the variables that they know. Right. Fine. And let's say, suppose if somebody has said length. Okay. So then my next probing question is, I would say that to assign a value for length or to explain the concept of length, I would say that do you require thermodynamics, or are you using the concept of length in thermodynamics?
Okay,
so good. This thermodynamics, in a sense, it's just high school thermodynamics, because as I understand, this high school physics also has a lot of thermodynamic chapters, physical chemistry, and so on and so forth. My point is, as a pedagogic principle, I would trigger them to think, and they should be able to tell me, no, these are the variables I know, but I certainly don't get exposed for the first time in thermodynamics. I have already known this in some other course, but I just used it here.
Okay.
And then I would say, okay, now this is a word coined as primitive. And I say that that's just a terminology that we assign to those variables that are not per se from that discipline.
So we should also remember that the quantities that we are going to be calling primitives in thermodynamics will be essentially accepted as they are and as they are defined elsewhere in physics. For example, in mechanics, we have the notion of kinetic energy and velocity and so on. And likewise from electricity, charge, current, voltage is something that we are aware of. So those are the quantities that we will call primitive. And thermodynamics, as has been explained in the video, accepts those as they are. Okay, thanks. That was useful. Right. So let me pose a few more questions, and then I will request someone to comment on this. The main one of the main things that has been pointed out in these first 6 lectures is the concept of a thermodynamic state space. And I hope all of you have gone through the discussion in these lecture videos when the thermodynamic state space was introduced. So my question is, the way the thermodynamic state space has been introduced, is this again something new in the sense that were you aware of this idea of introducing the state space and also the further uses of the state space, namely, what does it mean if I point out a specific state point in this state space? So, Dr. Vanjara, do you have a raised hand on this one?
Yes, sir. Am I audible?
Yes, please go ahead.
Sir, as my background from chemical engineering, so in chemical engineering, we do have plotting the various parameters, pressure versus volume, pressure, temperature, and especially the latter part of the PVT behavior of the substances, where we do locate them in the 2 dimensions. We do locate the properties in the 3 dimensions in our second course of chemical engineering thermodynamics, where we do go for the composition and all those stuffs. But the word thermodynamic state space that is separately introduced over here was certainly new for me, and I have got an idea that how actually a state can be represented in a different manner, and that's what the new thing I came to know from this.
So related to the thermodynamic state space, the notion of thermodynamic equilibrium, as it has been introduced in this specific set of lecture videos. I am assuming that when you guys used to talk about thermodynamic equilibrium, you had certain notion associated with what is meant by thermodynamic equilibrium. Whereas in this specific set of lectures, along with the notion of the thermodynamic state space, thermodynamic equilibrium has also been introduced. So any comment on that, in the sense that were you aware of this way of introducing the notion of thermodynamic equilibrium? What does that mean? And so on. Professor Jaishankar, do you have a raised hand on this?
Yes, sir. Sir, good afternoon, sir.
Good afternoon. Yeah, please go ahead.
Yeah, sir. Usually my background is civil engineering department. Sir.
Okay.
Okay, here it is. I want to calculate the coefficient of thermal expansion for pre-stress concrete as well as RCC concrete. But you are in the introduction slide, you are not discuss about the civil engineering department, where you are introducing how to calculate this thermal expansion. The details and all I left out. I'm not here with this. So because I have the little bit work on the project work is left regarding this coefficient of thermal expansion of alpha. If you have given some clear idea about this.
No, so don't worry about that part. What I'm trying to pose here is the question on simply the notion of introducing thermodynamic equilibrium with respect to the use of thermodynamic state space. So we have first introduced what is called as the state space, and now we are introducing when we call a situation to be in thermodynamic equilibrium, when a state is considered to be a thermodynamic equilibrium state. So the question is only on that.
Okay,
Just
sir.
hold on a
Please.
second. Mahendra, do you have a raised hand on this?
Sir, this is Mohammed Junaid.
Just hold on. Hold on.
Okay.
Mahendra, do you have a question? Maybe not. Yeah, please go ahead.
So first of all, let me introduce myself because unfortunately the morning session was missed by me. So regret for that. So this is Professor Mohammed Junaid from SVKM Institute of Technology, Dhule. Okay. So I just gone through 6 lectures and I just looked at the concept of steady space. So that was also a little bit newer concept for me. First of all, let me know whether can I interrupt in terms of question? Is that the proper format or am I going against the protocol?
No, that's fine. You go ahead. We will tell you that.
Okay. So actually, before this, I was preparing the subject in a way that at the initial level, I was going through the Gibbs phase rule, and according to that, there was equation of P plus F equal to C plus 2, and based on that, we are trying to fix the number of independent intensity property of a particular system, which are required to be fixed. And according to the number of phases, components, and all that, we can fix the state. And compared to that, this state space concept are a little bit not comfortable for me.
So my point was that once you are done with this workshop, and once you have realized that these concepts have been introduced in a certain manner, eventually you will realize that none of these ideas that have been introduced in this specific set of lectures violates anything that you probably knew from your earlier literature and so on. So that is the point that we would like to make here, that presently what we are just trying to understand is how many of these ideas are new to you, in the sense that the introduction of these words and how a certain situation is described. For example, in this case, this thermodynamic equilibrium and so on. Eventually, you will realize that once you have gone through this entire course, you will realize that none of the material that's been introduced in this course really violates anything that really you knew. So that's the only point I wanted to make. If Professor Bhandarkar is around, let me request him to also add on to this.
No, I think that's fine. We basically are looking at things slightly different from what most standard textbooks do. And it's not that this is the best way to do it. It's just that, over, I think, a long amount of time, we figured out that this is a good way to do it. And you can always come up with another way, but it has to be consistent. So the method that we are using here is that each definition is brought in such a way that it is consistent and you do not give out these circular definitions. So either whether it is with this thermodynamic state space, or let us say, of course, I think the first 6 lectures don't cover the first law still, but most textbooks jump into the first law with talking about work and heat transfer, etc. And then they define heat transfer in terms of temperature, and later on they define temperature in terms of heat transfer. So it's kind of a circular definition that they resort to, and which we do not want to do. We want to bring in each concept separately and then say this is by itself, either it depends on everything that we have defined up till now, and then it has to stand by itself. That's how we are progressing in this course. So primitive is something that we have decided is something which is totally known to us beforehand. And then once we introduce this concept of thermodynamic state space, at least we introduce this equilibrium concept without involving any of the new variables that we will bring forth later on. But once we bring forth later on, there is going to be no ambiguity as far as what the thermodynamic state space is going to be. So whatever we bring in, we want it to be unambiguous. That is, I think, the point that has to be made. Thank you.
So there is one comment that has come up in the chat. Vamsi Krishna Chaudhary. So it refers to something called as a microscopic approach. Okay. My question really here is the thermodynamic state space that we have just talked about, and the representation of a state on the state space. Do you think it has anything to do with the microscopic approach per se?
Hello, sir. Can I speak?
Yeah, go ahead, please.
Yeah. Sir, actually, it was like I had not thought that Professor Gaitonde will define thermodynamic equilibrium after defining thermodynamic state space. Because generally in the book of chemical engineering, the thermodynamic equilibrium is separately defined, like there is no presence of any tendency toward the change of the state of any substance or any system. So this is a different way to define the concept of the thermodynamic equilibrium from the thermodynamic state space. That's what I have realized.
Okay.
Otherwise, we do define it as a even not absence of change, or rather we do define it as even there is absence of any tendency to change the state of the system.
Yeah, so the way it has been defined here really technically does not violate the notion that
Yeah.
you talked about as well.
Yeah.
Okay, so it's in some, that's the thing that I was trying to point out, that nothing that has been defined here really violates any standard understanding of phenomena. Professor Gaitonde himself has a raised hand, so let me request him to go ahead.
Hello, may I say something?
Yes, of course, please go on.
Okay, see, this is an idea, or the idea of a state space, the idea of a state, and the idea of thermodynamic equilibrium are all related to each other. It's not necessary that you define the state space first and equilibrium later. They have to be defined and understood and appreciated simultaneously. I found that for further development of the course and the topics in thermodynamics, it is most convenient if the concept of equilibrium is defined in terms of our ability to represent a state on a state space. Because the moment it is a point, well, then all the properties of a point in geometric space are applicable even in thermodynamic state space.
So in this context, I would like to describe an example which we normally talk about with our students when we are talking about this thermodynamic equilibrium and the state space which has just been defined. So, you can consider our standard piston cylinder arrangement, and the gas, let us say some gas, which is contained between the piston end wall and the cylinder end wall, is our system under consideration. And let's assume that the gas is at certain pressure, say 5 bar, for example, whereas the ambient pressure is, say, 1 bar, roughly. And now, if we let this gas expand, there are different ways of letting this gas expand. If we let the gas expand very rapidly, okay, without any constraints whatsoever, and if we want to try to keep measuring the pressure inside this gas as the gas is expanding, what will you imagine will happen? Whether our pressure sensor will be able to provide a unique value of pressure for this entire system that we are considering as it expands rapidly. Only if, let us say, we have a situation where our pressure sensor is able to show a unique value for the pressure for the system as it is expanding in this specific case, we will be in a position to call the situation to be in thermodynamic equilibrium. Correct. So the comment that is coming up in the chat is quite useful. The value will depend on the location of the measurement. But let us say we have several pressure measurement devices in the along the cylinder wall and so on. So we are in a position to measure the pressure simultaneously at various locations. Suppose there is a discrepancy in the sense that different locations are showing different pressures, then we will not be able to call this system as it is expanding to be undergoing states after states in thermodynamic equilibrium. And as the comment is correctly written by Junaid, it will be a non-quasi-static process. So that's the next point that anyway we would have come to when we say certain process is quasi-static and when certain process is not quasi. These are all related ideas. So Professor Bhandarkar, do you want to add on to this?
No, not really. I think you can go ahead.
Okay, so that's fine. So here is where we wanted to point out that perhaps this way of introducing the notion of thermodynamic equilibrium is something that may not have been seen by the participants in the past. And we just want to make sure that this is something that is going to be consistent later, as Professor Bhandarkar said, with the notions that you already are aware of, what is meant by an equilibrium state and so on. So now, since somebody already had pointed out a quasi-static and non-quasi-static process, a quasi-static process has been defined with reference to the state space and how you represent the quasi-static process on the state space. So is this something again that everyone was aware of, that what is really meant by a quasi-static process? Is there some sort of a notion that people had in mind that quasi-static process has to be necessarily quote unquote slow process? Is that something that probably was in the mind?
Hello, may I speak, sir?
Yeah, please go ahead.
Yeah, actually, sir, we feel the same difficulty while delivering the same concept in the subject of thermodynamics to our students. Actually, students are feeling difficulty to realize or to understand exactly about the quasi-static and non-quasi-static processes, and especially while they try to solve the numerical problem based on it, then sometimes even I also feel that stuck up in the numerical, and it will take more time to solve this. So I request that kindly please elaborate a little bit more regarding these quasi-static and non-quasi-static processes.
So of course, this was explained in the lecture videos, how we want to define a quasi-static process with respect to the state space and the equilibrium that we have just talked about. So in fact, I will want to ask one of the participants if they would like to, based on the lecture videos that they have seen. So let's consider our gas in the piston cylinder system that we were talking about, and it is undergoing an expansion, let us say. Now, whether this expansion process to be called as a quasi-static process or not is something that we want to answer. So how would you like to answer it based on the lectures that you've seen so far? So someone is saying quasi-static process is a very slow process. And this is precisely what I asked, whether this condition has to be satisfied for a process to be considered to be quasi-static. Let us say I want to show this process on the thermodynamic state space, the expansion that I was talking about, gas in a piston cylinder situation. So I have chosen the state space to be of pressure and volume, let us say, and I mark the initial state I as a point, which means that it is a equilibrium state, and then I mark the final state again with another point somewhere in the state space. Obviously, it's an expansion process, so the pressure has dropped and the volume has increased. So you need to be careful on where to show the initial state and the final state. But the moment you represent these with points, what we are going to be essentially conveying to the students is that both the initial state and the final state are states of equilibrium, and therefore they are uniquely defined in terms of their pressure and volume values. So that's for sure. Now, as the system goes from the initial state to the final state, whether it has followed a quasi-static process or not is something that needs to be shown on this state space diagram. So how will you show it? So the notion that I'm seeing from some of these comments on the chat is that there is that slowly, evolving in terms of time issue that is coming into this definition of quasi-static process, which, whether it is true or not, is the question. Yeah, so the system must acquire equilibrium continuously is the right way of thinking about this. What we are essentially going to say is that between the initial state and final state, we can think about a large number of intermediate states that the system is going to go through. And if each of those intermediate states, as many as you can think of between the final and the initial states, are states of equilibrium, then you can actually form a locus, a continuous line, which can then join the initial state and the final state going through all these intermediate states. And if such a process is possible to be shown, then that process is going to be called as a quasi-static process. So there is no notion of slowness or fastness that really needs to be brought in terms of what is going to be considered to be a quasi-static process. So this is what I will at least mention and leave it at that for you guys to think about. Let me request Professor Bhandarkar to add anything if he wishes.
Yeah, I mean, I think that says about the definition that if I can go from an initial state to a final state through, or let's say, I mean, if I can actually say that every state out there in between state can be defined to be in equilibrium, then I will say that is a quasi-static process. And in our notation, I mean, we want to make it very clear to the students that if the process is quasi-static and every state is in equilibrium, then we actually join those two states by a clear solid line, showing that we knew exactly which path it took because every state was in equilibrium and hence every state is defined. If the process was not quasi-static, we say, okay, in some places we did not know the properties at all, okay, there was no thermodynamic equilibrium, in which case we tell the students that they should join the points by a dotted line from the initial to the final state. And the dotted line does not represent the path taken by the system. It is just saying that we do not know and hence we are drawing a dotted line. I mean, that is the convention that we try to force on the students, that if you don't know the path, then just join the two states by dotted lines. Else, if you know the path, then definitely it went through a series of equilibrium states and hence we can now join them by a solid line. So that's what we try to emphasize to the students. Yeah, thanks.
So now I would like to ask the participants, if they have thought of any questions on this much material that has been covered in the lectures 1 through 6, that you can pose to the students in order to test the understanding of these concepts so far. So Dr. Vanjara, do you have something here?
Yes, sir. Am I audible?
Yes, please go ahead.
Sir, I have actually kept the question in the chat box also. When I was looking at the videos from Professor Gaitonde, he has defined system A and system B rather than calling the conventional terminology of system and surrounding. So even in one of the lectures, sir has drawn the system A with a specific boundary and system B with a specific boundary, and then he has told about the thermodynamic interactions between the two systems. And later on, the same system B was actually renamed as surrounding. So generally, what we do is, even in later on we introduce first law of thermodynamics, we do introduce system plus surrounding as universe. So one question which I was having in mind at that time, that why to confine the region of the surrounding by stating it as another system B and not calling it like system plus surrounding as universe. I think, sir, you got my question, what I want to discuss about.
In fact, Professor Gaitonde himself has a raised hand, so let me request him to go ahead.
Yes.
This system surroundings thing actually is a misnomer, because the moment you say what is your system, then if you define surroundings as whatever is without the system surrounding it, then we are not defining the so-called surrounding system properly, and hence we tend to neglect it. Okay? Whereas for proper analysis of thermodynamics, we need two systems interacting, and hence I call it system A, system B. It is our choice to call system B as surroundings. Calling it surroundings has the danger of confusing this with our normal English word of surroundings. Well, that is something surrounding us, we need not worry much about it. That is not true in thermodynamics. To analyze the interactions, we need to know the state of the surroundings. To define the state of the surroundings, we must have the surroundings as a proper thermodynamic system. Hence, I believe that when two systems interact, we better call them as system 1 and system 2, or system A and system B. If then, after defining them properly, if you say, let us call system B as our surroundings, that's perfectly okay. And somebody mentioned that we define system and surroundings as a universe. Again, using the word universe is a dangerous thing, because universe has different meaning. Statistical universe is different from a physical universe. The philosopher's universe is different. The artist's universe is different. The poet's universe is different. We will also use the word universe, but that will be used after the second law, and that will be properly defined, and it will have absolutely nothing to do with our physical universe or the astronomer's universe. The reason for redefining some things in this course is just to see to it that we are not confused and we are not confusing ourselves or our students. That's it.
Okay. Thank you, sir.
So let me quickly try to address one question in the chat box, at least, from Sanjay Geji. What practical examples can we give from real life so as to make students realize or appreciate quasi-static process? So the answer really is that none of the real life processes can be truly quasi-static, because it's really difficult to generate a truly quasi-static process wherein the system is undergoing a large number of states which are in thermal equilibrium. But most of the problems that you see in real life, including the expansion of a gas in, say, a piston cylinder sort of an assembly, can be approximated to be a quasi-static process. More than anything else, the quasi-static process is an idealization or an abstraction that we utilize in thermodynamics in order for certain calculations to be done, which will provide us some benchmark results. So that's the way I normally, try to point out this issue with the students when it comes to the notion of quasi-static process. Let me still ask Professor Bhandarkar to provide more comments. But in fact, Professor Gaitonde has already written something which is what I was describing in some sense a few minutes back.
No, I have nothing to add.
Yeah. So I think one observation over a period of years used to be that students, keep reading all sorts of things, of course, before they come to engineering. Some things that they have understood correctly, some things that they haven't. But one way or the other, many of these names or terminologies is what they have understood, or rather seen, and they have some notions associated with that. Is the objective of this specific set of lecture videos has been clearly define what is meant by what, and that's what we need not think about anything else, anything else other than what is being described. And that's what I think we want to emphasize here, that the quasi-static process is only to do with a system undergoing, you know, a large number of equilibrium states as it goes from, say, initial state to the final state. So the last comment by Ms. Prajakta Kane is correct, that it is as close to equilibrium, you know, at all times, the system, as it goes from the initial state to the final state. Whether it goes slow or fast or whatever is not really an issue at all when it comes to the notion of the quasi-static process. What it helps is what Professor Gaitonde just wrote at 239, if you see the message. It's a model that we use to analyze the details of a process. So once you are in a position to represent a locus on a state space such as PV diagram or so, you can do, you know, analysis of that process further by performing, say, some sort of integrations and so on, as we'll see a little later. So that's the real utility of defining this model, or, you know, called the quasi-static process. So that's something that we normally try to explain and spend sufficient time on with the students.
Hello.
Yeah, go ahead.
Yeah. So this is not in connect with the quasi-static process, but I'll just take on to your previous question on what should be asked to a student to decipher whether he has understood the concepts pertaining to the topic 1 and 2. I'm taking a very basic thing on the states, that there are states, like for example in thermodynamics, described by the coordinate points of PVT, or it could be any combination, which is what is called as one distinct state. But this workshop being like pedagogy, how to elucidate this from student, two examples I would like to share with all is, maybe one is, let's say if we have served hot coffee or hot tea or hot milk, and you just keep it for some time, maybe just 10 minutes, right? And that it will become a slightly less hot coffee or a less hot tea. And I'll just ask the student, now is both the coffee at, let's say when I gave you at 2:30 and the coffee at 2:40, is it the same, right? Now this will make the students to think, and the most expected answer could be in terms of temperature they are different. Otherwise they will just say it's the same coffee, cold, and so on and so forth. And we can build on this discussion to elucidate that the thermodynamic state of the coffee that was served at probably 2:30 when it was hot, and when it became colder eventually by transferring energy to the surroundings without telling these words, is a different state. And another quick example is something like when we soak, like for example, pulses, dal, or sabudana, right, in water, their size increases because they just swell, right? Leaving aside the temperature change, it's just the change in the volume of that system. This is something, again, we can be asked a student as a descriptive question, as a scenario, and we can try to build on that so that they can unearth that thermodynamically it is a different system over a period of time. Time evolution is what they see, but what is happening inside is the thermodynamic state itself has got different, because otherwise in terms of temperature it's much more easier. But I thought like we should also give examples which are common examples which one can see around to bring out this concept of states as such. Thank you.
Yeah, let me just make one comment here, that the second example that you talked about is still something that we won't get into, in the sense that we are talking about for the longest period in this course, we develop all these concepts with reference to a closed system where there is no possibility of any mass transfer across the boundary of the system. So with reference to a fixed mass is what we really are developing the concept mostly. Your second example, of course, will involve transfer of water across the boundary, if you can imagine that around. So it's a different than what we are presently talking about in terms of the systems being closed systems.
Rather, I would say that if I can add, that is something like from that example, we can build on to just say that the concept of system itself is very arbitrary. It depends on what we want to focus as such. This is what Professor Gaitonde would have also told in an example showing a water bottle, that how many different ways you can draw a system with the same thing that you see it, right? And again, with the same system, depending on where you put your boundaries, the people will be able to appreciate or probably bring out that there is some transfer that is happening. And that is how, like, then we can introduce the word, okay, we need to assign a name for it. We just need a terminology for it. And the terminology that we have is the word open or closed. Thank you. Thank you.
So one point that I would like to mention here is going back on the classification of being primitive or basic or derived, as was introduced in the lecture video. We are beginning this course only talking about properties, and as you can imagine, even the next set of topics which you will go through, the first law will be introduced before the zeroth law. With reference to the discussion on the first law, nowhere there is a mention of temperature that we will bring in. Okay, so the idea here has been that you build upon the previous knowledge as you move into the course, starting from the primitives, and then use the thermodynamics laws itself or themselves to define certain properties, which are going to be called as basic properties. So as a preview of coming at I should mention that as a consequence of the first law, we will end up defining a basic property called the energy, and more specifically the thermal energy. And as a result of the zeroth law, we will define the property of temperature, which will, in our scheme of things of developing this subject, comes after the first law discussion is over. And then eventually we go to the second law, where using the second we introduce. So that's the way we want to progress in some sense consistently and without resorting to any circular arguments, as Professor Bhandarkar had said. So that's also something that's you can keep mentioning throughout the teaching, which is what we do, at least. This is what we make students understand the logical progress of how these topics are developed. So anybody else wants to share any question or any problem that they have come up with based on these first two topics, lectures number 1 through 6?
Professor Puranik, regarding the example which was stated regarding the coffee, even we have actually quite a similar concept, except we talk about the Newton's law of cooling. So we know that during cooling process, the temperature actually never reaches the equilibrium state. It actually follows in sort of a exponential cooling kind of a thing. So towards as it approaches the final temperature, the two temperatures, the profile comes very, very, very close. And that can be considered as a quasi-static process. So that's one of the examples that we, while teaching, give for a quasi-static process.
Okay, so here is where I will make a comment that because we haven't even bothered to introduce the property of temperature, we will still refrain from using any such example so far. So as far as possible at this stage in the course, we will try to invoke examples which will involve only a set of primitive properties, so that unless and until we have unambiguously defined something like temperature, we don't want to get into that. Okay, so that's normally how we do it.
Okay, sir.
You'll keep seeing how the course develops. and you will realize how temperature has been defined in fact the next set of topics where you'll go through first law and zeroth law lectures, you'll realize how temperature has been defined, and you'll realize that the temperature has not been defined initially at all, but in terms of something else which you otherwise would do differently. So that's something that please keep in mind. We'll come back to it later, when we talk about zeroth law and so on.
Okay, sir.
Santosh Rao, I think your question has been answered, but by Professor Gaitonde. Let me point out that this is actually an important question in the sense that again, students, during their 12th standard, maybe preparation for JEE or whatever else that they are up to, have heard of this terminology called the reversible process. Okay. However, we need to keep that word completely out till now. So as Professor Gaitonde has mentioned, only when we talk about and introduce second law of thermodynamics, we will introduce the notion of a reversible process. And we will try to then, also point out whether a reversible process needs to be quasi-static or a quasi-static process needs to be reversible or whatever the case may be. Okay. But as of right now, as we are going in these so-called baby steps, the only baby step that we have covered so far is defining the quasi-static process in a completely unambiguous manner. All that we want to inform the students is that as long as I have a set of equilibrium states through which my system goes as it goes from initial state to final state, we will say that it has undergone a quasi-static process. That's it. So absolutely no notion and use of the word reversible and so on will be brought in. So so all those other issues that are being written, namely whether it is necessary for a reversible process to be quasi-static and so on, we will come to it when we formally introduce and define a reversible process only after the second law discussion has been initiated. So please keep that in mind. It's actually very important aspect, and that's the reason I wanted to mention this, despite the fact that Professor Gaitonde has already written a few comments in the chat box. Professor Bhandarkar, do you want to add to this?
Yeah, not really. I mean, I think this is really sufficient, this much. Yeah.
Okay, so one more point that I would like to bring here is toward the end of the first 6 lectures, an entity called a point function and then an associated notion of an exact differential is something that is brought about. So anyone wants to comment on that? So the group part, I would request the workshop staff to take care of. So you can talk to Mr. Mahendra Parmar on that.
Sir, may I have one question about quasi-static process, please?
Yeah, please go ahead.
Sir, correct me if I'm wrong. Whenever we are measuring any property, that means by default we are assuming that that particular process is a quasi-static. Am I right? Or
say that again? I'm sorry, actually I didn't hear the last.
Whenever we are measuring any property, let's the same example you just discussed. Let's say there are some pressure sensors.
Yes.
And we are measuring the pressure. So whenever we are measuring any property, so that means we are assuming that that particular process is basically a quasi-static process.
Well, that's a good question actually. So let me try to, at least the way I understand this, let me try to answer it, and then I'll request Professor Bhandarkar to correct me if my understanding is. If we, for example, choose that gas in a piston cylinder sort of an assembly where it is expanding, and then we have a bunch of pressure sensors, let us say, on the cylinder wall. And at every instant, so to say, we are measuring this. Now, each pressure sensor, as it is located at a particular position, will indeed show some value, isn't it? It will show some value of pressure. But what we are talking about is for the entire system of this gas contained between the cylinder end wall and the piston face, is whether this entire system is undergoing a quasi-static process, in the sense that at any state during or any stage during the expansion, whether the pressure, for example, for the entire system can be represented by a unique value or not. That's what is supposed to mean by the entire system undergoing a quasi-static process.
Yeah, so I think basically the fact is that if you're going from state A to state B, if at every point, let's say you are measuring the pressure, let's say at every instant you could get a unique value of pressure and any other quantity that you wanted, let's say temperature too, then you are saying, because I can get a unique value of pressure and temperature at every instant of time, that means the system was in equilibrium because it's unique. I can actually put a dot on the thermodynamic state space. If I could not have measured it, then I could not put the dot. Okay, so for example, if the pressure was varying throughout the system, then it's a hazy thing. I mean, nowhere is it a unique value. I cannot put a dot on the thermodynamic state space for that particular instant of time, and then it is no longer quasi-static. So that is how we would like to look at quasi-static. Yeah, anyone with some other kind of question?
Hello.
Yeah, please go ahead.
Good afternoon, sir. Sir, we always study about thermodynamics. What about thermostatics? I posted one question, and in PK Nag I've read that about thermostatics. So we always study about thermodynamics. So can you tell me the right answer or right approach?
I think, maybe Professor Gaitonde can.
Okay. See, the thermodynamics is the historical word. Okay. And we states equilibrium because we are able to study them, we are able to define properties, we are able to define relations between properties and so on. Now the thermodynamics, the word dynamics is considered parallel to the dynamics in mechanics. Now the question is, what is statics?
Yes, sir.
In mechanics. There is no such thing as statics in thermodynamics. Thermodynamics is simply a word. It is not thermo followed by dynamics. Consider it as. Now, if you say states of equilibrium are so-called static states, it's a matter of definition. And hence, you'll say, okay, thermodynamics should be called thermostatics, and maybe they will call heat transfer should be called thermodynamics. This is only a matter of nomenclature. Let's not get into it.
Okay, sir. Thank you.
So there is a question related to fluid mechanics and thermodynamics in terms of the pressure. So anyone wants to address that? Not that we want to get into the fluid mechanics discussion at all. We are talking about pressure as, really is mentioned in fluid mechanics as well. It's the same pressure that we are talking about.
Sir, hello. I have one question for Gaitonde, sir.
Yeah, please go ahead.
Sir, can you just briefly describe what is the concept of continuum and what is the difference between the concept of continuum in thermodynamics, and we study always continuum concept in fluid mechanics. So what is the difference both subject point of view? Because this is the question in which students are already confused. What is the concept of continuum?
Yeah, let me in the meantime answer this. It's the same continuum that we are talking about, whether it is thermodynamics or fluid mechanics. What essentially we try to convey to the students is that we are not really going to be bothered about the molecular structure of the material that we are dealing with, and it will be assumed to be continuously distributed in space, and the properties of interest that we are going to be looking at, say pressure or temperature or density and so on, are some sort of statistically consistently obtained numbers, at points of space. So we don't really get into the molecular description of gases or liquids and so on. So in that sense, the continuum that is used in thermodynamics is essentially same as that used in fluid mechanics. There is absolutely no difference.
Okay. Sir, can you tell me any live or real example of concept of continuum by which we gave the concept to students that they could really in easy way the students could understand? If any example
So
of
the regular engineering fluids that you utilize in any standard processes are all in continuum. The gases that we deal with or the liquids that we deal with in any application like internal combustion engine, power plants, etc. They are all in continuum state. Only if you start dealing with extreme high vacuum sort of situation where there is very highly rarefied state of a gas, you may have to deal with a non-continuum situation. But otherwise, bulk of our engineering applications that we deal with on a regular basis utilize fluids that can be very well, that can be meaning that they are always in the state of continuum.
Sir, is there any similarity between continuum and macroscopic approach?
It's the same thing. It's exactly the same thing.
Same thing. Okay, sir.
Let me try to address one question here. Something has been written out here in the chat box related to isothermal, adiabatic, isochoric process, and whether each of these is quasi-static. So what exactly is meant by this? My answer is that each of these can be a quasi-static, or each of these can be a non-quasi-static.
Sorry, sir, can you repeat?
There is a question at 301. Isothermal, adiabatic, isochoric process, which we haven't really talked about yet, whether they are quasi-static processes or not. The point is that any of these can be either quasi-static or non-quasi-static. Quasi-static is something that we have defined clearly as the one that undergoes a sequence of equilibrium states, and so each of these processes can be a quasi-static process. That's what I wanted to say. Okay, so there is a good question here from Dr. Piyush Vanjara. What is the difference between postulates, premises, and laws? And I think request Professor Bhandarkar to address it, because this is something that we actually talk about in the course.
Yeah. So can TKG classes please mute yourself because it is creating. Okay. So I think Professor Gaitonde, of course, explains this better. Finally, a law is something that you start everything by making a statement, okay, about the universe. You observe and you make a statement. And premise is something that you say, I have made a statement, and beyond a point, I am not going to have too much to say about it. But postulate is something that we believe that we think it is always true, okay, and only if the postulate has been distilled clearly through many let's say I would say different situations, and we realize that never has it failed, I think you elevate it to the status of a law. Otherwise, you always start with a statement, and what you call a law is really something that seems to have passed too many tests, and we believe it to be true. And of course, you must realize that this is just a fine distinction we make. There is no guarantee that any of the laws will suddenly start failing. We can believe that the first law and second law are always true in thermodynamics, and this is as far as what we observe of the universe. But we don't know whether this is really true everywhere, because we haven't seen everywhere, let us say. Similarly, the Newton's 3 laws of motion, they were elevated to the status of laws, and we believe that they were totally, you cannot remove them from the pedestal that they were. But that really cannot be said completely once you bring in relativity. So you should realize that these are statements that we've just made some fine distinctions, and laws are something that we will apply, reasonably mercilessly as far as we are in our course. We believe that they are always true, and we will do the same thing with postulates too. Professor Gaitonde wants to add something, then I think.
Sir, there was another thing also in this particular session that was regarding the assumptions. And Gaitonde sir has explained assumptions along with the premises. So that has also created some ambiguity which I would like to make clear.
I forget what was written. Professor Gaitonde, are you there?
I am there.
Yeah.
So can I say something?
Yeah, please, sir.
Yeah,
Okay.
yeah, please.
See, let me put the assumption, premises, postulates, laws. They belong to the same set. That something which we cannot prove and we assume to be true. So all of them are in a way assumptions. Okay. Now, some of the assumptions we make to restrict ourselves to a smaller domain. Otherwise, we will have too much on our head. Right? Those assumptions are usually we call premises.
Okay.
Premises, for example, a system is a continuum, is a premise, because that simplifies it. We can remain in the classical phenomenological continuum thermodynamics. We don't have to worry about individual molecules and particles. So that way it's a premise. Now, once you decide on premises, we restrict our domain, and in that domain, we cannot progress unless we make further assumptions. So there are assumptions regarding behavior of systems, assumptions regarding how systems behave. For example, a common premise is that a thermodynamic system, when left isolated in that situation, eventually reaches thermodynamic equilibrium or a state of equilibrium. Now, this is not a postulate, it is a premise. We know it generally happens, but once in a while, if a system remains in a state which cannot be called a state of equilibrium for a long time, so be it, no law of thermodynamics is likely to be violated because of this. Now, hardly any difference exists between postulates and laws, except that laws are on a higher pedestal than postulates. That's it. So we have these three laws of thermodynamics in some order, 0th, 1st, and 2nd. And we have some other state postulate or state premises or state principles, which for some reasons have not become laws. But you give up one or more of those premises, and then our structure of thermodynamics becomes quite loose. It doesn't remain robust enough. But for some reason, I don't know why, some postulates have remained at the postulate level. There are some laws, some postulates have been promoted to the so-called laws. There is no organization or a committee which decides this. This has happened over decades and centuries. That's it.
Okay, thank you, sir.
Sir, I have one question.
Yeah, please go ahead.
So all the quasi-static process must be a reversible process. Is it so?
No. So let's not talk about reversible process notion at all for now.
Yes. Yes, sir.
We will formally introduce, meaning the lecture videos will introduce what is meant by a reversible process only after the second law has been, introduced. And at that point, we will try to address the question related to the reversible process and quasi-static if required. Okay, so let's please wait till the second law part is taken up.
Okay, sir.
Yeah.
Sir, may I interrupt?
Yeah, please go ahead.
Sir, regarding the introducing the concept of reversible and its location, or at which lecture it should be introduced again, isn't it a debatable issue? Because in some books, in the basics, And before introducing the first law of thermodynamics, the reversible and irreversibility of a process is introduced. No doubt, if we look at the depth of the second law, there also we are having the concept of the reversibility and irreversibility is important to the same extent. So where it is better to introduce from the student's point of view to make it easy to understand.
So if I can,
sorry, Upendra, let me complete and then
Yeah.
you can go. So we think that the way it has been introduced after the second law discussion is initiated is the most convenient place where it can be introduced from the student's point of view. So till then, till the time we address matters related to first law, zeroth law, and so on, you'll realize that there is no real requirement to introduce the notion of a reversible process. Only after the second law statements have been introduced, we bring the reversible process discussion, and that's where I think we think it is convenient to. Yeah, sorry, go ahead now, Upen.
Yeah, so it's basically the same thing. Maybe I'll tell it in different words. That this is a sequence of topic introduction that we believe is convenient. Okay, there is no let's say harm in introducing a sequence which is different as long as you are consistent. Okay, so you must be consistent. You must realize that if I introduce a topic for a certain reason, okay, it should not be based on something which students still don't know about, and unnecessarily you are making some kind of circular argument. So we do not feel the need to introduce reversibility till the moment that we begin the second law discussion. And there too, we think it is the most appropriate place. Of course, when we come to it, we'll tell it. But there is this whole concept of irreversibility and production of entropy. All that is directly connected as one single topic, and that's why we would prefer to introduce it at that time. And there's no need for it anytime before that in the sequence that we are going. If you want to follow a separate sequence which is consistent, there is nothing wrong with that. That's all. Let me just stop at that. Yeah. I also wanted to ask. There is a question in the chat, the last one, which says, "Are the laws of thermodynamics universal? Are they valid in outer space, out of Earth?" Well, no one knows. Until you go out there and experiment, you will never know. None of the laws that we see on Earth can be truly be told that there would be. You can go somewhere, a million light years from here and still think that they may be valid, because we don't know. So unless you go there and do it, let us not assume anything. I mean, it's just an assumption that they may be valid everywhere, but whether it's true or not, we do not know. Okay, so the laws that we will talk about are what we see here being valid on at least wherever we are, not anywhere else. Okay, thank you.
So the question that is coming up, the last one in the chat, properties of the system. Remember, temperature is something that we haven't really talked about. So when we introduce the notion of the state of the system, that time itself you can introduce the notion of properties, and that's been done in the lecture. So I would request you to view the lectures. Okay.
And again, I think someone is asking whether the entire universe can be considered as an isolated system. Okay, let's get into this. When you say universe, I think you mean the astronomical universe. Okay, so now again, we absolutely don't know about it. Okay, so the answer is clearly we do not know. Okay, we do not know the extent of the astronomical universe. So let us not get into the place where the entire universe can be considered as an isolated system. But if we are talking of a thermodynamic universe, then you can say the thermodynamic universe is actually an isolated system that we are bothered about. It is not the astronomical universe. Okay.
There is also one question on how thermodynamics is applicable on radiating system. So I do not understand exactly what is meant by a radiating system, but if it's a heat interaction that you are referring to through the means of thermal radiation, And as far as thermodynamics is concerned, the laws of thermodynamics as what we are discussing presently, which we will consider to be applicable where we are and where we do our business, will be applicable equally to a system which is dealing with heat interaction through radiation. So as such, there is nothing new that you need to invent in order to analyze a system which may have heat interactions because of thermal radiation. As long as we are within the realm of the premises that we are not violating, I think the laws of thermodynamics will apply, and there is nothing new or different that you have to. So there is a question on isolated system. An example of an isolated system. So what can be an example of an isolated system?
So I don't know if this is something that you want to tell students, Mr. Junaid. See, by definition, an isolated system is something where we say that there is no, let us say nothing crosses its boundary, neither mass nor energy. Okay, so it's a concept we have invented, and you can always idealize many systems like this. You can always invent a boundary where you say that you have insulated it to such an extent that there is no let's say any energy crossing the boundary, neither any mass crossing the boundary. So it's a concept that you have made. Okay, he want a real example. Unfortunately, just like quasi-static process, etc., there is no real example that we can provide. Okay.
Yeah, it's again an idealization that is used for making certain analysis convenient. And by invoking such idealizations, such as say the quasi-static process, or now that we are talking about this isolated system and so on, at least we can make some progress in terms of predicting something. Whether real life is obviously going to be close to that or not is not really the issue that we think about presently. But at least to go somewhere to get some predictions done, we bring in these notions, these idealizations, and use the predictions then as some sort of a yardstick or a very highly idealized situation based on which you can make progress on the real life applications. That's the way normally these things are to be considered. Yeah, it's in a way it is hypothetical. So we have
Sir, may I ask? Hello, sir.
Yeah, please go ahead.
Actually, sir, what I have found in most of the books, some standard books also, I have found at least two examples of a system. One is the universe. And as per the Big Bang theory, universe is expanding. So there cannot be the isolated system, because if it is expanding, that means obviously not isolated system. The second one is something like having some perfect insulation material. So that too, we have not yet got anything which can be called as a perfect insulation. That was actually what I was looking. So really, we do not have anything which can be called as a perfect insulation.
We are talking about the universe, and if you are referring to the astronomical universe, we really do not know. So things which we are not really sure about, we should not make any statement about either, whether that is to be considered as an isolated system or not. And the other example that you yourself mentioned, that there is no such thing as a perfect insulation. So precisely that's the point, that these idealizations are brought in to make sure that our analysis of the systems can proceed somewhere, and we can get some useful indications from our analysis in terms of the predictions of how the system is going to behave and so on. And then we need to use those predictions with some common sense when it comes to real life analysis and building of systems. That is really the bottom line on any of these engineering science disciplines.
Then, sir, I cannot understand if something for which we do not have any real life example, then why we have lot of contents based on that particular concept. Lot of questions, lot of content from the syllabus. Any comment on this, please?
I didn't understand actually what Professor Bhandarkar did it.
Yeah, I think what you're trying to say is why do we introduce it? Well, that is because we need to analyze certain things, and unless we make a certain set of assumptions, we cannot go ahead with the analysis. Okay, so that analysis gives us a reasonable, let us say, picture of what is going on, and not the exact picture ever. So, but for analysis purpose, we need to make certain assumptions, and this is just one of those.
So in fact, let me add on to what Professor Bhandarkar said, and that probably is one of the most important things that we need to keep reminding our students of. Oftentimes when it comes to, for example, these laws, students seem to think that it is something which is, for the lack of any better words, I will use the words God-given, and therefore they have very strange notions about these things. I have had student in my class say that Newton's laws are essentially, in some sense God-given. The point is that's not what it is. So these are, as Professor Bhandarkar explained, Professor Gaitonde explained earlier, these are formalizations that we ourselves have come up with based on the observation of how phenomena happen in the world around us and so on. And that part needs to be emphasized to students right from the beginning. And in the same vein, I will say that many of these assumptions, such as a quasi-static process or the isolated system that we just talked about and so on, should also be mentioned in the same sense that these are idealizations which are highly useful in carrying out certain analysis. In absence of those, many times we will not be able to go anywhere. And if we are not able to go anywhere, then we will not be able to do anything, of course. So the idea is that with these analyses, we can go somewhere. And then, when it comes to building of real life systems, as yardstick, analysis, these are helpful. That's really what we should be constantly emphasizing to our students. So as a formal requirement, you will be asked to submit a question or a problem, based on the topics that we have covered so far as part of that assignment. So please think about something that you think will test the understanding of students, and submit it according to the schedule that has been provided.
So this needs to be covering topic 1 and topic 2, isn't it, sir?
Yeah, you will be told where to submit the assignment.
Yeah, if you have a question still, you can ask them. It is as answered. It is on the IIT Bombay X webpage, I think. But you can ask the workshop staff.
Sir.
Yeah, please go ahead.
Sir, there is one graded activity mentioned in the course. There the space is given to submit our activity and the questions. I think at that location we should submit the questions which we asked over here.
No, of course, that those also can be the questions that you can submit. But the idea was that we have, in principle, now covered topics 1 and 2.
Yes.
Till now, which cover lectures number 1 through 6 in that lecture series.
Yes, sir.
The idea was, based on this much material, if you want to test your own students on this much material so far, would you be able to generate one question or one problem, let us say, which will address one of the ideas or the concepts and so on that have been discussed so far? And that is what we are expecting you guys to submit, because that's where the pedagogy aspect comes in. That when we want to teach thermodynamics in a certain fashion, certain ideas, certain notions are getting introduced. And to make sure that those ideas and those notions are understood by the students, we need to invent and generate questions or problems. And we want you to do the same thing and then submit those as part of that graded activity. Is that clear?
Sir, it is mentioned in the graded activity that submit the questions or problems based on material topics 1 and 2 And additionally, it is written that you are expected to submit the questions or problems created only during the group activity sessions.
No, that you need not, consider that seriously, in the sense that if you, while we were undergoing this discussion for the last 1.5 hours, if you think that, you have generated a question or a problem based on what has been discussed so far in the last 1.5 hours, you can utilize that as well. That's not a problem. As long as you think that the question or the problem that you are going to be generating is going to be utilized as a good question to test some of the understanding of the topics that we have covered so far, as far as the student is concerned.
Yes, yes, sir. Yes.
Is that fine?
Yeah, sir.
Yeah, please go ahead. Who is that?
Sir, this is Anandan, sir. Actually, can you please elaborate on this? What we are supposed to do? In the topics you said. After seeing that video, you said we have to create some questions or problems and present, and you said we have to submit. So can you please elaborate on that, sir? Actually,
that's exactly what I was doing. But let me say that again. So now, in principle, again, we have covered topics number 1 and 2 rather, based on lectures 1 through 6. And what are the topics that we have covered so far? So these are basically introduction of the subject, the introduction of what is called as a system, for example, introduction of what is called as a surrounding environment. Then we have undergone the classification of system. Beyond that, we have introduced the state of the system, right? And while we are introducing the state of the system, we have also introduced the notion of a property of the system to describe the state. After that, we have also gone through the state postulate 1, and then this important notion of thermodynamic state space and thermodynamic equilibrium. And also we have talked about what is called as a quasi-static process, so, and non-quasi-static process. So these are the based on what I have noted down, these are the ideas, notions, and concepts that have been covered so far. And the idea is that based on this much material, can you think of one question or one problem, if you wish, which will test the understanding of any of these questions or any of these rather ideas or concepts when posed to a student? That's what we are expecting you to generate and submit. Okay. Thank you. Yeah, so let me also mention here that I think Professor Bhandarkar has already mentioned a few times that certain established textbooks introduce and develop this subject in a certain fashion, and just because these textbooks are quote unquote established, we often really don't think about that. We essentially go by whatever has been presented to us in these textbooks. But what we have found is when we try to do that, students in the class start posing questions, and those questions then end up making us aware that certain things have to be introduced in a certain unambiguous and non-circular fashion. So we cannot utilize concepts which have not been formally introduced to talk about something which is being done right now. Okay, and that is how over a period of years the current set of lectures have evolved, and that's what we really want to point out to the participants, that this is one way that the current set of instructors from IIT Bombay think that it's a very non-ambiguous, clear way of introducing the topic. But clearly, because you have been reading books and you have been referring to various published literature of all kinds, you will realize that this sequence may sound or may look a little bit different. But the point is that at the end of it, we want to think about it from the student's point of view, that what is going to be the most clear, most unambiguous way of doing things. And at least, we think that this is one way of doing it. And that's really, I'll keep emphasizing this part throughout the workshop. Of course, that doesn't mean that we are forcing each of you to do it exactly in the same fashion. Once the entire material is covered, you may think about, coming out with your own sequence in terms of introducing topics and notions. The only, requirement in a way is that it should be in an unambiguous fashion, in the sense that you should not utilize notions which are yet to be introduced to talk about certain present stuff. That's really the only bottom line, I think. And I hope, Professor Bhandarkar, I have summarized the objective of this workshop here.
Yeah, I think that's correct. Yeah.
Hello, sir.
Yes, please go ahead.
Sir, as you told in the previous session also, that the pedagogical aspect involves that how to teach the thermodynamics theoretically well in the classroom. The main problem which we do face is students find they have a fear for understanding thermodynamics. So our task is to create interest. So one question I posed initially also, is it a proper way to introduce initially with the definition, the scope, the domain, the applications, and along with limitations of the thermodynamics, so that it creates interest in the students initially? Because what happened, they do believe that this is a hypothetical subject having more idealizations, and the things will not be applied in reality. And again, it becomes difficult to understand, especially tough concepts like fugacity and all those which are coming later on. So that's what I'm searching for a way. Is it proper to introduce in the first lecture all this stuff?
So one way of addressing this issue can be that the first couple of lectures can be spent only on showing, schematics or photographs of real life applications.
Yes, sir.
And for example, since I am from mechanical engineering and all my co-instructors are also from mechanical engineering, I suppose my limitation would be to quote applications of mechanical engineering. But depending on your field, you can broaden the scope. What one can do perhaps is, before we actually get into any of these formal discussions on the concepts and so on, maybe close to first 2 lectures, if not 1, can be spent on simply showing photographs of, say, internal combustion engine, or a gas turbine, or maybe a boiler, or some power plant sort of an equipment, or refrigeration systems, air conditioning systems, and
Yes.
many other things which utilize principles of thermodynamics as the basic ideas on which the whole machine is built. Of course, there are mechanical aspects on building these machines, but the specific applications that I talked about, and then there are many additional ones that you can bring in, base their design on fundamental thermodynamic principles. Okay, and that is what you can probably try to show initially in the first couple of lectures to at least get the attention of the students that, okay, if I want to, for example, design a turbojet engine, I better understand how to employ first law of thermodynamics and possibly second law of thermodynamics as well. So you can try to grab the attention of students using a nice cutout photo of say a turbojet engine, but at the same time you need to make the students aware that to achieve that end goal, you have to begin with the A, B's and C's, and those A, B, C's are what we are going to be doing in this class or in this course. That's probably one way of addressing this aspect. Let me request Professor Bhandarkar to comment on this.
Yeah, I mean, that's a pretty nice question, in the sense that Up till now, we were talking about how to make the course unambiguous. So we were talking of a sequence of topics which would make it unambiguous. But to make the course interesting is another pedagogical aspect, which is a reasonably tricky subject. But yes, we do this. That we and to tell you the truth, a lot of students do get attracted to the concept of automobile engines because they think that this is the closest thing to mechanical engineering, especially if these are mechanical engineering students. I'm sure the chemical engineers can come up with a topic which excites the chemical engineers. So you can always say, how do I analyze the IC, automobile engine? In fact, it's such a perfect piston cylinder system. And then you say, if I want to figure out how much work it does or what is the amount of power it delivers, how much work it does, I will need to go through a set of steps. I need to do a set of proper analysis. And for that is where this course starts from. And of course, this is right in the beginning, but I must tell you that everywhere, a new concept is brought in, you may have to probably, come up with the right example, which, and in many places we have, turned ourselves, especially when we are talking of thermodynamics, we have turned ourselves to IC engines and power plants because these are things which the students seem to be excited with. Okay, now if whether they're really excited, we don't know, but this is at least this seems to be the right approach for us.
Yes. Exactly, sir. This happens in our chemical engineering branch also, that the applications are like in phase equilibria and chemical equilibria to know the maximum extent of reaction and separation, that is unit process and unit operations. Ultimate is like destiny is thermodynamics. That's a very broad sense the applications are, which actually when we introduce this thermodynamics brief, rather in the fundamentals in the first course of thermodynamics, when we introduce this to the students, they are not aware in depth about the branch. And so sometimes what happens, they do not have clear-cut aspects that what I need to do with this subject. If we can connect that very good initially, like I have seen a very good a small video in the course itself, which creates interest for the students to teach these subjects. But sometimes for specific branch, again the things will be elaborated in detail.
Yes. So you're absolutely right. That little video is very nice actually. It captures the attention of the student, and indeed that is something that something of that sort you can think about. Additionally, of course, nowadays so many animations, so many videos of these end applications that we talk about relevant to our field are available on something like YouTube, for example. Now, of course, whether those are permissible to be used for academic institutions use in a class or not is something that we need to figure out. But as long as that is not a problem, you could utilize that as well. That also is oftentimes quite catchy for the student, initially at least, to get the interest going. And then of course, then you need to keep emphasizing that eventually to reach that goal, you have to carry out certain analysis in certain steps. And what we are going to be doing is the first level analysis here in this class, which is what Professor Bhandarkar was saying.
Yes, sir. Thank you so much.
Yeah, sure. So Professor Gaitonde, this video is embedded. It's the video of or which is at the introduction of your ME209X.
Yes.
Junaid, sorry, you had a intro video.
Yes, someone has raised a hand, I think. Sharada Shani Garab.
Yeah, please go ahead. Ms. Sharada, please go ahead. Okay, so let me we will wait for Ms. Sharada if she wants to ask that question. In the meantime, let me point out that tomorrow the first session, which will be in the morning 9 to 11 a.m., will be a session similar to what we are doing here. And there we will actually be covering the notion of work interaction along with the first law and the zeroth law. So I will request all participants to go through that material on the course webpage, the lectures. and then have your own thought process put in place for the discussion on that. And similar thing will be expected in the sense that if you can come up with one question as part of that graded assignment process on those topics. Is Miss Sharada here? She has a raised hand. Yeah, anything, either descriptive or a small numerical example that you generate, which will test any of the understanding that we are expecting from this set of topics. Yes. Okay, I think, well, in a way, if not the complete solution, at least what we are expecting is if you can at least provide a small description of the response or the answer that you will expect from the students on the question that you are generating, that is good enough, even if no detailed solution is provided. Ms. Sharda, no, if you have spoken, we have not been able to hear you. Yeah, so as Professor Gaitonde just wrote, key points in the solution process are expected. That's actually a nice way of putting it.
Hello, sir.
Yes.
Sir, there is one problem solving disciplinary method, I think, discussed by Professor Gaitonde.
Yes.
Yeah, regarding first, a specific procedure is given that we have to list down the all values and draw the sketch and let us arrive at the solution, and then at the last interpretation of the answer. But I have learned a different way of attempting a problem, and that not to focus on what is given, to focus on what is required. Sometimes it happens that this is fine that in examination we do give the data which is required only, but sometimes it happens that there are some database, some properties which are given which are not required. So can't we focus reverse? This is just a debate. What is required, and for that, what are we can go for reduction of the problem. For this, these are the sub properties which is required, and finally arrive at the solution.
I think technically that is what really Professor Gaitonde meant in the document that he has come up with. There may be a bunch of other information that may be available, but we need to understand what is the problem statement.
Yes.
And as we are understanding the problem statement, we need to start noting down those things correctly and carefully.
Yes.
That is all that is really mentioned. I think Professor Bhandarkar wanted to probably answer this. So go ahead.
Yeah, I don't think anywhere was it said that you must focus on unnecessary things. You must figure out what is listed, and then you must figure out what is necessary. I mean, to look through that maze of data and try to figure out what is necessary is really the key. Okay, and a lot of times people hurry and they say, oh, these two quantities are given, I need to do this, whether they are necessary or not is not so that is why you first read. I think you need to read the question well. You need to figure out whether a process diagram needs to be made, because a lot of times just drawing a clear and perfect process diagram ensures that more than half the question is solved. Okay, so I think that is what the procedure outlays. And another thing I think it emphasizes is conversion of units, and which a lot of people don't seem to pay good attention to. And I can tell you absolutely, conversion of units is something that we must all pay attention to, because you can get into a lot of problems otherwise. Yeah.
Yes. It was introduced fantastically. Like a method was given to attempt any problem.
Yeah. So the advantage of that specific procedure is that it is universal, in the sense that the same process then can continue for subsequent courses of, say, fluid mechanics or heat transfer or whatever the case may be. And that is why I think it is good to introduce it right at the beginning, where maybe a third semester engineering student is getting introduced first now to thermodynamics, so that problem solving discipline is a universal process in some sense, and it's very nice to implement it right from the beginning.
But just I would like to say that in especially the problems of the engineering design, we do follow the reverse sequence, like what we require, and for that which equations we do have, and in those equations which properties we do require, and then we go reverse that whether those things are given or we need to assume.
I see. Okay, but here the way
that's what I was telling. That's nothing else.
Anyway, but I think we have tried to explain what we mean by following that process.
Yes, exactly. But it is also very fantastic. We can explain, we can utilize that for the students, because students are having their main concern about the numericals also.
Correct. That's the point that Professor Bhandarkar just mentioned a few minutes back.
Yes,
people seem to be in great hurry often, the students that is, to do something, but oftentimes that gets them into a tangle, and that's the reason this systematic procedure has been put forth.
Yes. Thank you, sir.
So Mahendra here this side.
Yes, Mahendra, go ahead.
So sir, actually we have followed it up with the participants who were not attending today's morning session.
Yeah.
So I have found that there are about 5 groups like this. I'll just mention the group number. Group number 1, group number 5, group number 14, group number 16, and group number 19. So these are the 5 members who are individual right now. So like they are the single person in that group.
Okay.
So sir, with your permission, if I may put them in some other group, would that be fine?
Oh yeah, absolutely. Please go ahead. You need not ask for permission. Please go ahead.
Okay. So sir, what I would suggest is like the person from group number 5 and 14, they should club with group number 1. So my colleague Sanjay Kharat will be sending them the mail that this is the new group for them, and group number 16 and 19, no?
Yeah.
So we will add them since there is 2 group members in group number 3 and group number 4. So
you can try to equilibrate the numbers, according to how the registrations are right now. That's absolutely fine.
Okay, sir.
No problem. You go ahead and figure out what is the most reasonable combination from your side.
Okay, sir.
Yeah.
So I will just send them the mail only to those participants who have been shifted to the new group.
Yep, sounds good.
Yeah. So the other housekeeping announcement was like there were participants who have not filled the attendance in the morning session. So I urge all the participants if they should ensure and fill up the attendance. This will help us understand like how many of you are attending and not. And anyways, we have to submit this report to the TechWhip also. So all these informations are required, and for the final certification, we will be factoring the attendance also.
Yeah, so I will request all participants to follow these guidelines, please. And if Mahendra, if you need to make that attendance sheet available again for the morning session, please do so. Please do that. Yeah.
Okay.
Yeah.
I will do that, sir.
Okay, so with this, then we can wrap this session right now. And I hope tomorrow morning, 9 to 11, we continue in the same manner, essentially, and take up the topics as I mentioned, work interaction in the first law and zeroth law. I think the specific topics and the number of lectures, etc., has been mentioned in the schedule, so you can go through that. So thank you very much, all of you, and we will see you tomorrow morning at 9 a.m. Thanks a lot. I'll see you tomorrow at 9.
Okay, thank you very much. Thank you.
Thank you, sir.
Thank you, sir.